Good morning, dear students. Hope I am audible.
Yes, sir. Good morning, sir.
Thank you, Arpita, for confirmation. So we'll start today's class. Okay. So today's concept is HDFS block architecture. Yesterday we have seen Hadoop 1.0 used to store block size of 64 MB, and Hadoop 2.0, the block size was 128 MB. So how exactly Hadoop works in the same line we'll discuss, and we'll continue further. Okay. I think yesterday I have been telling. So Hadoop has a very powerful ecosystem, and the entire ecosystem is totally based on HDFS, because the data has to be stored on HDFS first. So based on this, the other technologies, maybe Storm, Scoop, HBase, or MapReduce, or Yarn, or Pig, Hive, Spark, whatever, Uzi, Mahout, whatever it is, Zookeeper, whatever it is. So everything is totally based on Hadoop core component. So Hadoop core component is what we see, the distributed file system. Everything is totally based on Hadoop distributed file system. That's very important. And Hadoop distributes the file. It will not store in one single computer. It will store in multiple computers. So that is the concept. And that too, Hadoop store the files in terms of small chunks called blocks. So it will store the file contents in terms of blocks. So this is what we have understood in the previous class. Now, so Hadoop has the concept of blocks. So 64 MB for by default in Hadoop 1.0, and of course, like file size, file system, a single disk file is Hadoop. HDFS breaks the file into small chunks, block sized, equal sized chunks, and which are stored as independent units. And these independent units, we call it as HDFS blocks. And these blocks, by default, it is replicated 3 times. The replication factor of Hadoop file system is 3. That means it will maintain 3 copies of each block. 3 copies of each block. Right.
Excuse me, sir.
Yeah.
Sir,
Hello.
I have a doubt.
Huh.
Isn't our memory wasted, sir, when we maintain 3 copies of data?
This was the question asked by many of the people. Many of the people. So they ask, but they are not worried about memory wastage. They are worried about security of data. So, of course, memory is wasted 3 times. But how do you provide fault tolerance? So when you want fault tolerance, definitely you should have a backup always. Okay. So considering all those things, definitely Hadoop maintains 3 copies by default, and it has been universally accepted. So if you want to have fault tolerant system, error free system, definitely you should maintain a backup. So whenever you maintain a backup, definitely extra memory you have to spend it. So your point is correct, but apart from this, there is no other option. So fault tolerant systems, if you want to build, definitely you should have a copy, backup copy. So by default, Hadoop maintains 3 copies. So if you really concerned about memory, if you are really, so you can configure. So by the default one, you can configure it to 2 copies, or you can configure to a single copy. So when you make it single copy, there are high risk. So if the block, block is damaged, I think you don't have any option to recover it. So, and that too, you are running entire Hadoop system on what do you call commodity hardware. So commodity hardware, you can expect any time to crash. But when you are not having 100% sure that commodity hardware will work perfectly, so definitely you make a copy. Always you keep a copy. So even if it is a very important thing, what you will do, yeah, even though you are not worried, so your Aadhaar card or whatever copy, you will keep it in email one copy, you keep it in pen drive one copy, so that it is very important for you. You are not worried about the memory wastage. So it is just like that. Okay, so it maintains. Okay, so when it comes to the error tolerance, space will not come into picture. Of course, your point is correct, and it has been discussed in many of the discussion forums, Hadoop forums, Hadoop conferences. But finally, they have accepted for Hadoop to maintain, you know, three replicated copies. So that's what the justification at this point I would like to give. And you want still more, secure system. So if the second copy is also lost, if the third copy is also lost, so for such people, you can maintain many, replicated replication factor. You can increase to 4. You can increase to 5. That means you can have more 4 or 5 copies. So that is also there. So if it is very important, you will maintain not 1, 2. You will maintain 4, 5. So that is also there. So they are not worried about the extra space. They are worried about the importance of the data. So it's all depends upon the person to person, organization to organization. You can configure your entire Hadoop system. Okay, so that is one very important thing. And I told Hadoop 2.0, the default block size is 128 MB. See, if a file of 612 MB is given to Hadoop system, what Hadoop does, Hadoop splits the entire file into 128 MB, 128 MB, 128 MB, 128 MB, and last is 100 MB, because 128 into 4 is 512, 512 plus 100. So uh, uh, 612 MB. So the entire file is divided like this: 1, 2, 3, 4, 5. So 5 different blocks are maintained. One file is divided into 5 different blocks, and these 5 blocks again they are replicated. Every block is replicated 3 times by default. This is how it stores. And remember, what happens, these blocks, when you divide the file into blocks, and these blocks are given to your name node. Name node is one which will generally distribute these blocks across various data nodes. So it will tell which block has to store in which data node, which block has to store in which. Name node is just like manager in a form. So if a file comes, this particular block has to go to which section or which data node. So that just like that, it will give a indication which name node has to, which block has to go to which data node. The decision name node will take. And as you see, so the blocks are replicated in 3 different replication. 3 blocks are repeated. So that is a very important thing. So that's what your name node, what it will do, it will maintain the data. It will maintain the data record, that is, it maintains the metadata of all the blocks. So, and all these blocks will be maintained by your name node, and names of the block, names of the file where it is stored, and it will also hold uh, which block is stored in which data nodes. So, and it will maintain the three, replication factor. Observe here a simple example. Block B1. There are three blocks: B1, B2, B3. Observe now. B1 appears in three times: 1, 2, and 3. You see, it is available in data node 1, data node 2, data node 4. So whereas B2 also same thing. B2 is data node 1. So B2 in data node 3, B2 in data node 4. So every block you see, B3 is also B3 here 1, here 2, here 3. So every block is maintained 3 copies. It is maintained 3 copies. Even B5, you see B5, B5, B5. So you have and uh, how exactly your data node is actually maintains the rapport with name node is, it every 1 second it will be sending a heartbeat. Heartbeat means the block report. So I have all these blocks, and these blocks are with me. That report it is sending. So which is called block report. Block report is also called as heartbeat. So every data node will send heartbeat every second, and this block map will certainly holds all the block report heartbeat information. A particular data node, if it doesn't send the heartbeat, okay, it understands, oh, there is a problem with that particular data node. The entire data node is crashed. So what happens? Immediately it refers to the namespace, where in the namespace it contains all the metadata. So example, take this is data node 1, data node 2, data node 3, data node 4, data node 5. Data node 3 has lost data node 3 has lost all the uh, data node 3 has lost the heartbeat, and when it has lost the heartbeat, so automatically what happens, your name node will understand, oh, data node 3 has lost, that is something happened with respect to your data node 3. So data node 3, what are all the blocks that were there in data node 3 will be kindly mute. What are all the blocks that were there in the data node 3 will be repaired, or will be automatically regained from other systems, so that will be done by your name node. So name node maintains the namespace, and data node maintains the data space or block space. So namespace is nothing but it is holding all the details, names, and which block ID, where it is stored, in which data node it is there, and remember, these data nodes are computers. And your name node is also a computer. Name node is just like a manager which maintains the metadata, and metadata contains your hierarchy of the files, file blocks, block IDs, and where these block IDs are stored. So that is the information that exactly name node will have. The relation between name node and data node is always very important. So name node is the one which actually maintains all the data in the data node. And another thing, very important thing that you should understand, heartbeat and block report. If heartbeat and block report doesn't reach the name node at regular interval time, automatically name node will sense the failure of a data node immediately, without any second thought. What it will do, it has all the data block details about a particular data node. Here data node 3 data node 3 is, gone now. It is gone. So automatically what it will do, it will create, based on the replication, the details of data node 3, it will create another computer. It will prepare another computer. Whatever that was there in the data node 3, it will be prepared within no seconds, within no time. It will immediately create. And data node 3 is created by your namespace or name node, with the other copies of the blocks. It will automatically create data node 3. So automatically that will be handled by your name node job is to see that all data nodes are working properly. If something goes wrong with the particular data node, automatically it will create another data node that has the failed data nodes data. So these failed data nodes data, it will recover from other replicated blocks. It will create, it will recover it, and it will create another computer with this. And your name node has all the capabilities to create data nodes, maintain data nodes. And so that is one of the finest architecture that Hadoop has. So Hadoop is so popular because of this. Hadoop maintains the data nodes automatically. The name node maintains the data nodes automatically. If some data node goes out, it automatically creates another data node. Parallelly, it restores with the other copies and makes it ready for further computation. So that is one of the good technology that we are having. And benefit of doing such blocks. The first benefit is the most obvious. The file can be larger than any single disk. So what happens, it can easily fit on the network. So any size file you give, so irrespective of the file is split into small blocks, and each block is stored in multiple computers. If 3 computers are not sufficient, it will automatically switch on another computer. It will make another computer to on, that is another data node to come up, and it will automatically on, it will automatically scale down. Of course, anyhow, all these computers are there in rack space. Rack space in the sense, all these computers are stored in a rack, and each rack is actually blade computer or blade server or blade data node. They are like small boxes kept in racks. Okay, so you can't imagine. I'll show you at the end of this class a small video wherein all these computers are stored in a rack, just like files, just like files they store in the our bookshelf. How we store books, the same way it is stored in a rack. The computers are stored in a rack, and each computer is interconnected with the network. So if you want only data size is only very less, it can accommodate only 4 computers. For our previous example, the file size is 612 MB of file. So the file needs only 1, 2, 3, 4, 5 blocks. So it used to use only 5 computers. If the file size is more, it will use 5, more computers. If the file size is less, it will use less blocks, less computers. So that task is done by your name node. Name node splits the file and stores. That is the first job. Second job, it maintains the all data nodes health. And if some data node is not performing due to network failure or some issues, automatically it will create based on the metadata what it has. Based on that, it will create another data node parallel to the failed node. So automatically it will create. So that's how it maintains the entire Hadoop ecosystem working perfectly. That's why we call it as Hadoop is a fault tolerant system. So everything is maintained by your name node, and data node is actually holding the data. Data node holding the data, name node holding the metadata. Metadata is nothing but the summary information, or the information about all these blocks, which block, where it is stored, in which computer it is stored, which computer second copy is stored, which computer third copy is stored. So all those information is stored, is recorded in this metadata, and this metadata is maintained by your name node. So that is what we call it as namespace. Namespace is nothing but your this one. So second advantage is, there is nothing that require the block from a file to be stored on the same disk. So they can take the advantage of any of the disks on the cluster, and it's very, very important to see that it will never store the file or file blocks as a single file. It will never store in only one computer. It will store in multiple computers, and that too it will store in different computer, different rack. So why it stores the second copy in different computer, different rack? Because if the computer fails, okay. If the entire rack fails, what happens? If the same rack, if you maintain the second copy also, what happens? That is another problem. Okay, if the entire rack fails, you will lose the data node also, the secondary copy also you will lose. So what it will do, your name node is so intelligent, it will never store the second copy or the third copy in the same rack. It will store in different rack. This is what you call it as rack awareness with respect to replication. Rack awareness. Rack awareness is nothing but it will never store the same file in the same rack. It will store in different racks with respect to the replication is concerned. So that is what you have. In fact, it would be possible, if unusual, to store a single file on HDFS cluster whose block is filled, all the disks in the cluster, and of course, so you can certainly move on to the other clusters. Easily you can do it. So further, the second one is make the unit of abstraction to block rather than a file. Simplifies the storage system. Okay, when you use blocks, what happens? Your entire system becomes simplified, and you can certainly achieve parallel processing. File is split into blocks, and each block is stored parallelly in computers. And if the same, if you want same file, if you want to analyze for processing, so definitely what happens? All the blocks are simultaneously processed in different computers. So you will get much faster results. Parallel processing is happening. You will get faster results, faster outputs. So the benefit is the storage becomes very simplified. Simplicity is something to strive for all the systems, but is especially important for a distributed system in which failure modes are always so varied. So if something failed also, automatically you need not have to worry about the other part of the file. Only that particular block is failed. That block will be recovered. Easily it can be recovered with other two copies. It will always maintain the 3 copies. Even if there is a failure, automatically it see that the replication factor balance 3 is maintained. Okay, automatically it will maintain. And the storage subsystem deals with the block, simplifying the storage management. Storage management is very simple because the blocks are fixed in size. It is easy to calculate how many can be stored on each disk. So it becomes very easy for disk management also. How many blocks can be stored on each disk, and how many disks are required, and also very easy for the name node to maintain metadata. Eliminate the metadata problems, that is concerns. Blocks are just chunks of data to be stored. The file metadata such as permission information does not need to be stored with blocks. So another system can handle the metadata separately. Very easily it can be maintained. So both your metadata information can be maintained easily. Both the block data also can be maintained easily. So that is another very important thing that you should understand. So this is, these are all the benefits. Furthermore, block fits well with replication for providing fault tolerance and availability. I have already told replication. So replication factor is 3 by default. You can always vary. And to ensure against corrupted blocks and disk and also machine failure, each block is replicated to a small number of physical separate machines. So typically the 3, and while doing the replication, it sees that the same copy will not be stored in the same rack. This is what you call it as a rack awareness. So if the block becomes unavailable, a copy can be read from another location in a way that is transparent to the client. Yes, that's very important. A block is no longer available due to corruption or machine failure, can be replicated from alternate locations to other live machines to bring replication factor block to the normal level. So if, uh, for example, you take there is a system failure, and that system failure, when you fail that, when you have a particular data node failed, what happens? The replication factor of the blocks which are stored in that particular system goes down, and goes down by 1. So you will have only 2 copies. One copy is already lost because of system failure. So what happens? Hadoop creates parallelly another mirror. We call it as mirror data node. So mirror data node, in the sense whatever the failed data node blocks were having, so based on the metadata, it will create another data node, so which you call it as mirror data node. Automatically it will maintain the replication factor always 3. It always maintains the replication factor 3. Even if there is a failure, automatically that failure, it will create another parallel system and store all these blocks. It will bring up all the blocks, so that the replication factor is always 3. Always 3 in the sense every block is maintained always 3 times. Even if there is a failure, the failure, in order to overcome that failure, automatically it will create another copy of the block in some other system, and somehow it maintains replication factor 3. It is always bring it to the normal level. So that is another very, very important. And all these things are being handled by your name node. And similarly, some application may choose a set of a high replication factor. Suppose some application require replication factor 4, 5, 6. So beyond 3, yes, you can certainly configure, and it is also very important. And when you have more copies, you have advantages. You can do parallel processing. If somebody wants to read the file, yes, parallelly the same file can be read. Three people simultaneously can read the same file. Of course, anyhow, the principle of Hadoop system is write once. That means file can be created once, but can be read many times. So whenever you want to read the file for n number of times, yes, parallelly different people want to see, yes, it becomes very easy for them to see. So that is another advantage that we have. So here is a diagram. You can see how exactly namespace is maintained. Namespace is maintained like file name, the number of replicas, and block IDs. So every file name node maintains this file name. How many replications are there? 3 replications. How many are there? So you can see there is a file user Samir P. Data is part 0, that is the first block. Part 1, second block. And R2 means replication factor 2. R3 means replication factor 3. And the blocks IDs are 1 and 3. So this particular file is made into two blocks, and it is block IDs are 1 and 3. This file is made as 3 blocks, 2, 4, and 5. And observe here, so replication factor 3, part 1, that is block 2 will have 3 copies, 1, 2, and 3 copies. Block 4 also has 3 copies, 1, 2, and 3 copies. Block 5, ID 5 is also 3 copies, 1, 2, 3. Whereas for the block IDs 1 and 3 may have only 2 copies replication. So 1 and 1, that's all. You have only 1, 1, only 2 copies, because user has configured like that. Replication factor he has copied for only 2. So that is the thing. So that's how you can do. And if you want to check how many how many files are there and how many blocks are for each file, so you can certainly issue this command, Hadoop FSCK. FSCK means file system check is the command. From the root, all the files and all the blocks. It will list all the blocks that will make up each file of the file system. It will display. This is the command. And anyhow, we'll discuss this command, commands in our further upcoming classes. HDFS commands we'll discuss. So this is one command that will certainly display. Now I will have a small demo regarding what Santiago Supercomputer Center tell about Hadoop distributed file system. So I have a small video to demonstrate this. So kindly watch this video. Yeah.
The Hadoop distributed file system, a storage system for big data. As the storage layer, the Hadoop distributed file system, or the way we call it HDFS, serves as the foundation for most tools in the Hadoop ecosystem. It provides two capabilities that are essential for managing big data: scalability to large data sets and reliability to cope with hardware failures. HDFS allows you to store and access large data sets. According to Hortonworks, a leading vendor of Hadoop services, HDFS has shown production scalability up to 200 petabytes and a single cluster of 4,500 servers with close to 1 billion files and blocks.
So observe here. So these are all single blade computers. See, there are so many rack. This is first rack, this is second rack, third rack, fourth rack, fifth rack. So like this, many racks comprising of one cluster. Such hundreds of clusters will be there in one data center. So that's one very important thing that you should note and understand.
If you run out of space, you can simply add more nodes to increase the space. HDFS achieves scalability by partitioning or splitting large files across multiple computers. This allows parallel access to very large files since the computations run in parallel on each node where the data is stored. Typical file size is gigabytes to terabytes. The default chunk size, the size of each piece of a file, is 64 megabytes, but you can configure this to any size. By spreading the file across many nodes, the chances are increased that a node storing one of the blocks will fail. What happens next? Do we lose the information stored in block C? HDFS is designed for fault tolerance in such cases. HDFS replicates, or makes a copy of, file blocks on different nodes to prevent data loss. In this example, the node that crashed stored block C. But block C was replicated on 2 other nodes in the cluster. By default, HDFS maintains 3 copies of every block. This is the default replication factor, but you can change it globally for every file or on a per file basis. HDFS is also designed to handle a variety of data types aligned with big data variety. To read a file in HDFS, you must specify the input file format. Similarly, to write a file, you must provide the output file format. HDFS provides a set of formats for common data types, but this is extensible, and you can provide custom formats for your data types. For example, text files can be read line by line or a word at a time. Geospatial data can be read as vectors or rasters, data formats specific to geospatial data. Or other domain-specific data formats like FASTA or FASTQ formats for sequence data in genomics. HDFS is comprised of 2 components, name node and data node. These operate using a master-slave relationship where the name node issues comments to data nodes across the cluster. The name node is responsible for metadata, and data nodes provide block storage. There is usually 1 name node per cluster. A data node, however, runs on each node in the cluster. In some sense, the name node is the administrator or the coordinator of the HDFS cluster. When a file is created, the name node records the name, location in the directory hierarchy, and other metadata. The name node also decides which data nodes to store the contents of the file and remembers this mapping. A data node runs on each node in the cluster and is responsible for storing the file blocks. The data node listens to commands from the name node for block creation, deletion, and replication. Replication provides 2 key capabilities, fault tolerance and data locality. As discussed earlier, when a machine in the cluster has a hardware failure, there are 2 other copies of each block that was stored on that node, so no data is lost. Replication also means that the same block will be stored on different nodes in the system, which are in different geographical locations. A location may mean a specific rack or a data center in a different town.
See, data replication, it will be replicated in different data center as well as a different rack. So 3 copies means 1 copy is maintained in different rack, another copy is maintained in different data center. So all these things we will discuss in the next upcoming class. That's all for today's class. Thank you for attending.